What is matrix rank? The rank of a matrix is the maximum number of linearly independent rows, or columns it contains. Think of each row as a recipe. If some recipes can be made by mixing others, they are dependent. The rank tells you how many truly different recipes you really have. In engineering mathematics, rank is a measure of the amount of information a system of linear equations carries. It tells you whether a set of equations has a unique solution, infinitely many solutions, or no solution at all. A decision that directly influences circuit analysis, statics, control system design, and finite element modeling. Mathematically, for an M by N matrix A, rank of A equals the maximum of the number of linearly independent rows, which equals the maximum of the number of linearly independent columns. If rank of A equals N full column rank, the columns span the whole real N space. If rank of A equals M full row rank, the rows span real M space. This concept underpins ideas such as controllability in state space models and the solvability of stiffness matrices in structural analysis. There are three allowed operations that do not change the solution set of a linear system and therefore keep the rank unchanged. Row swapping R sub I swaps with R sub j. Swapping two recipes, like changing the order of dishes on a menu, the menu is the same, just reordered. Scaling a row, R sub I becomes k times R sub I where k is not zero. Multiplying a recipe by a non-zero factor, for example, doubling all ingredient quantities. The recipe remains the same dish, only the portion changes. Row replacement, R sub I becomes R sub I plus k times R sub j. Adding a multiple of one recipe to another, similar to borrowing ingredients from one dish to adjust another. The overall set of dishes does not gain a new independent dish. These operations are the tools we use to sculpt any matrix into a simpler shape, reduced row echelon form or row echelon form, while preserving its rank. Important effect: they may change the appearance of rows and columns, but they never introduce or eliminate linear independence. Hence, the rank before and after any sequence of elementary row operations stays the same. REF is like arranging books on a shelf, so that each new book starts further to the right than the one above it, and all books below a leading book are blank 0. The steps are: start at the leftmost column, find the first non-zero entry pivot in that column. If the pivot is not on the top row, swap rows to bring it there. Create zeros below the pivot by replacing each lower row R sub k with R sub k minus a sub k comma p divided by a sub p comma p times R sub p, where p is the pivot row and a sub k comma p is the entry under the pivot. Move to the next column to the right and the next row down. Repeat the process on the submatrix that remains. The resulting matrix satisfies. All non-zero rows are above any zero rows. The leading entry first non-zero of a non-zero row is to the right of the leading entry of the row above it. All entries below a leading entry are 0. The picture is similar to a staircase that climbs to the right. Each step is a pivot. REF is not unique. Different row swap choices give different REF, but any REF of a matrix will have the same number of non-zero rows, which equals the rank. RREF tightens the staircase. Not only are there zeros below each pivot, but also above, and each pivot is forced to be 1. Scale each pivot row so that the pivot becomes 1. R sub p becomes 1 over a sub p comma p times R sub p. Eliminate entries above each pivot using row replacement. For every row R sub I above the pivot row p, replace R sub I with R sub I minus a sub I comma p times R sub p. After these passes, the matrix has the following properties. It is in REF. Every leading entry is 1s. Each column containing a leading one has zeros everywhere else. RREF is unique for a given matrix. No matter which row operations you initially choose, the final RREF will be the same. This uniqueness makes it a powerful tool for reading off the rank and solving systems. Visually, RREF looks like a set of isolated islands of 1s, each standing alone in its column, with all other entries in those columns wiped clean. How to read rank from ref or RREFs. The rank is simply the count of non-zero rows in any ref or RREF. Since the transformations preserve rank, the number of rows that still contain a pivot after the staircase is built tells us how many independent rows or columns the original matrix had. In Ref, count rows that are not completely zero. In RF, count rows that contain a leading one. Each such row is automatically non-zero. Why does this work? Each non-zero row in Ref carries a new pivot that cannot be expressed as a combination of the previous pivots, exactly the definition of linear independence. Therefore, the number of pivots equals rank. Formula: rank of A equals number of pivot rows in Ref or RF. If you have an M by N matrix, the rank can never exceed the minimum of M and N. Example 1, 2 by 2 matrix A equals a matrix with first row 3, 6 and second row 1, 2. Step 1, use row replacement. Row 1 becomes row 1 minus 3 times row 2, resulting in a matrix with first row 0, 0 and second row 1, 2. Swap rows to bring the non-zero row on top, giving a matrix with first row 1, 2 and second row 0, 0. Row echelon form has one non-zero row, therefore rank equals 1. Example 2, 3 by 3 matrix B equals a matrix with rows 1, 2, 3 as 1, 2, 3, 2, 4, 6, and 0, 1, 1. Pivot in column 1. Row 2 becomes row 2 minus 2 times row 1, giving a matrix with rows 1, 2, 3 as 1, 2, 3, 0, 0, 0, and 0, 1, 1. Pivot in column 2. Swap row 2 and row 3, resulting in a matrix with rows 1, 2, 3 as 1, 2, 3, 0, 1, 1, and 0, 0, 0. 0 below pivot, already 0. Row echelon form has two non-zero rows, therefore rank equals 2. Example 3, 4 by 4 matrix C equals a matrix with rows 1, 2, 3, 4 as 1, 0, 2, negative 1, 2, 1, 4, 0. Negative 1, 2, negative 2, 1, and 3, 1, 6, negative 2. Step 1, pivot at row 1 column 1 equals 1. Eliminate entries below. Row 2 becomes row 2 minus 2 times row 1, row 3 becomes row 3 plus row 1, row 4 becomes row 4 minus 3 times row 1. The resulting matrix is first row 1, 0, 2, negative 1, second row 0, 1, 0, 2, third row 0, 2, 0, 0, fourth row 0, 1, 0, 1. Step 2, next pivot in column 2 at row 2 equals 1. Eliminate entries below. Row 3 becomes row 3 minus 2 times row 2, row 4 becomes row 4 minus row 2. The matrix becomes first row 1, 0, 2, negative 1, second row 0, 1, 0, 2, third row 0, 0, 0, negative 4, fourth row 0, 0, 0, negative 1. Step 3, column 3 has all zeros, so skip. In column 4, pivot at row 3 with value negative 4. Scale row 3 to make 1. The matrix becomes first row 1, 0, 2, negative 1, second row 0, 1, 0, 2, third row 0, 0, 0, 1, fourth row 0, 0, 0, negative 1 fourth. Step 4, eliminate entries above the pivot in column 4. Row 1 becomes row 1 plus row 3, row 2 becomes row 2 minus 2 times row 3. The final row echelon form, actually reduced row echelon form, has 3 non-zero rows. Therefore, rank of matrix C equals 3. These step-by-step reductions illustrate how counting pivot rows yields the rank. Skipping a zero column. If a column becomes all zeros before you have processed all rows, simply move to the next column. Do not force a pivot where none exists. Forgetting to swap rows, a 0 on the diagonal does not mean the matrix is singular. Look below for a non-zero entry and swap. Mixing up row versus column operations. Only row operations are allowed when computing rank via echelon form. Column operations can change rank. Counting non-zero entries instead of rows. Rank is about rows or columns with pivots, not the total number of non-zero numbers. Leaving fractions unsimplified. In exams, keep fractions tidy. A common mistake is to write 2 over 4 instead of 1 over 2, leading to arithmetic errors later. Time-saving tip: stop once you have identified the pivots. You do not need to finish the whole reduced row echelon form if the question only asks for rank. Just count the pivot rows you have obtained. Use the staircase visual, sketch a quick diagram of the staircase. Each step you draw corresponds to a pivot, helping you avoid missing one. Check with the dimension theorem. For a system AX equals B with A of size M by N, verify that rank of A is less than or equal to the minimum of M and N. If your count exceeds this, you made a mistake. When a row becomes all zero early, you can safely ignore the remaining rows below it. They cannot introduce new pivots. Remember, the rank is invariant. If you ever feel stuck, you can compute the rank of the transpose, swapping rows and columns, and the answer will be the same. Explanation: previous year exam questions with brief solutions. Question: B.Tech 2019 paper 2 . Find the rank of capital M equals a 3 by 3 matrix with first row 2, 4, 6, second row 1, 2, 3, third row 0, 0, 0. Solution: sketch: perform R1 swap R2 to place a simpler row on top. Then R1 is open bracket 1, 2, 3 close bracket. Replace R2 arrow R2 minus 2 R1 yields open bracket 0, 0, 0 close bracket. The row echelon form has two non-zero rows. First two rows are independent, third row is 0. Rank equals 2. Question B M.Sc Mathematics 2020 . Given capital A equals a 3 by 4 matrix with rows 1, negative 1, 2, 0, 3, negative 3, 6, 0, negative 2, 2, negative 4, 5. Find its rank without using determinants. Solution: sketch: use row operations. First step, R2 arrow R2 minus 3 R1 gives a row of zeros in the first 3 columns. Second step, R3 arrow R3 plus 2 R1 yields open bracket 0, 0, 0, 5 close bracket. Now the row echelon form is a 3 by 4 matrix with rows 1, negative 1, 2, 0, 0, 0, 0, 0, 0, 0, 0, 5. Two non-zero rows implies rank equals 2. Question C Gate 2021 Mathematics . If capital B equals a 3 by 4 matrix with rows 1, 2, 3, 4, 2, 4, 6, 8, 3, 6, 9, 12, determine the solution. Sketch: observe that each row is a multiple of the first row. After R2 arrow R2 minus 2 R1 and R3 arrow R3 minus 3 R1, you obtain 2 zero rows. Only the first row remains non-zero. Rank equals 1. Question D Civil Engineering 2018 . Find the rank of the stiffness matrix capital K equals a 4 by 4 matrix with rows 12, negative 6, 0, negative 6, negative 6, 12, negative 6, 0, 0, negative 6, 12, negative 6, negative 6, 0, negative 6, 12. Solution: sketch: apply row operations to create a staircase. After a few swaps and replacements, you obtain 3 non-zero rows. The fourth row becomes a linear combination of the first 3. Hence rank of K equals 3, indicating one rigid body mode as expected for a planar frame.